So I'm pleased to present today Professor David Grainger, who is from the University of Utah. He is here as a Fulbright scholar visiting the University of Otago for 4 months, and from what I understand, his tenure is almost complete, so he's here for about another week. So we are lucky to have him here up at Auckland presenting a talk today on translating academic research into commercial outcomes. So Professor Grainger is the University Distinguished Professor and the George S. and Dolores Dore Eccles Presidential Endowed Chair in Pharmaceutics and Pharmaceutical Chemistry at the University of Utah. His research focuses on drug delivery methods, implanted medical device and diagnostic performance, and toxicity of nanomaterials. He has published 185 research papers, 24 book chapters, mainly on biomaterials, innovation in medicine and biotechnology. And there's a number of research awards and honors to go with that. So I'll stop there and hand the floor over to Steve.
Thank you. Thank you, Vinod, and thanks to everybody for coming. I feel quite honored. I'm at the end of my stay at the University of Otago. It's been a wonderful experience for me in Dunedin, and I'm happy also to make this acquaintance with people in Auckland here as I leave New Zealand. There is a new mechanism in the Fulbright Foundation, so it's possible that I could get another award and come back, and if I do, I'll spend more time here. I'm sorry that this is at the end of my stay. But anyway, thanks for gracing me with your presence today. What I've been asked to talk about is about this unique environment at the University of Utah, which has enabled certain benefits for me personally and for my students, and for the translation of certain technologies from my lab as well as from numerous colleagues, and I'll try to talk about that. In the spirit of cooperation, if you have questions, please stop me at any time and we can discuss the content on these slides. So I have to disclose, this is university policy for me, I have to disclose some of my conflict of interest. There's a number of technologies that I might or might not talk about today depending on where your questions take me, and I'm required by my university to disclose my industrial affiliations. So here's my technology experience captured in one slide, and I'm not going to go through this in much detail, but simply to say that this for me started very early with a company that I started in 1993 as a glucose sensing company. It was sold to Bayer Healthcare, and I exited that company in 2008 after a series of very complex financial transactions to get a early stage technology actually into the human clinic. I was actually diluted 17 times, for those of you who are interested in the capital investment there. And then Bayer divested its technology. As you might know, you might have read that Bayer sold its diabetic healthcare unit 2 years ago to Panasonic, but Panasonic already had a sensor. So the founder of the company, who's still alive and had exited the business long ago, that started with me, my angel investor bought the company back from Bayer, interesting, and then flipped it and sold it to a Swiss company that makes glucose sensors, Debiotech. So that's an interesting translational story. Won't say more about that. 2000, I started another company out of my office in Colorado, and had another angel investor come with a shell company that's a publicly traded company that doesn't represent really anything except it's traded on the NASDAQ. And so then we did a reverse merger of my two-person company, me and my student, reverse merged into a publicly traded company and developed technology for 6 years and sold it to Schott, a German company that bought the technology, and then we used that cash infusion of $38 million to evolve into the new version of this, which is a publicly traded company currently on the stock market now. The story I'd like to tell you about is this most recent spin out called Elute about orthopedic biomaterials that I've created, and I'll try to get there as fast as I can. But another interesting story that occurred actually here while I was in Dunedin was a small company I founded that deals with ophthalmic delivery to the eye. The reason I'll be in pharmacy tomorrow is that Ilva Rippenthal here at Auckland University Pharmacy also does drug delivery to the eye. But I founded a very simple company with a colleague of mine who deals with high hyaluronic acid biomaterials. And we made a small product that, while I was here at Otago, sold to a publicly traded company, iGate in New York City. And so I don't even have the financial transaction papers. They're still in my mailbox back at home. So anyway, things happen in real life. They happen in real time. It's a very dynamic environment for me. And I'll try to tell you now why that occurs. So the typical university technology transfer process is actually very straightforward and boring when you think about it this way. So I'll try to walk you through the primary features of it. That is, it starts with the university scientist who thinks that they have an idea. This is the start of a problem. In the sense that many of the ideas that university scientists think they have, one, have already been thought of by somebody else, or two, are really just an idea, but there's no real value behind that idea. And the whole process then, from this box to the left until these boxes to the right, is the idea of trying to build value. No idea has an intrinsic financial value until you build a product that actually has a perceived value on the market. And in order for you to do that, you have to then, the university scientist has to perceive about what is the unmet need that somebody is willing to pay money for. That's the value of that idea. So just because a university scientist makes a discovery doesn't mean that that discovery has any value. And I would argue that up until even time you actually have a patent, you really have no value. And even when you have a patent, you've spent a lot of money to get that patent. And until you get that patent money back, by virtue of somebody wanting to buy that patent from you, you have no value. So there's a lot of people who talk about having patents, but in fact, there is no value to those until somebody really wants to buy them, or license them, or pay money for them. So the story starts with the scientist, but in fact, the scientist has to understand how you drive the discovery to the value proposition and get this thing then starting in the white boxes to produce value in the marketplace. So this is a story which I'm not going to talk about because it's actually wrote to every single technology transfer office. It's the topic of every single entrepreneurial course. I've lectured in the entrepreneurial courses in Otago, and in fact, every university teaches this slide. What's interesting is that because of this process, university scientists are now paired with technology transfer offices, and ironically, your office is in this building. I learned that today. And the technology transfer offices in most universities, their job is to help that scientist understand, one, how to build value with their idea. Two, is there something discoverable there that can be protected? Three, can the university take that protection, license it, and make some money for all parties involved? And four, is can we create value that benefits humankind in some way? What is interesting is that in our country we have 2,000 universities. Of those 2,000 universities, 300 of those universities have decided that they'd like to have a technology transfer office that facilitates this engine of discovery, this engine of value proposition creation. Someone want to tell me how many of those 300 offices in my country actually make money?
Not many.
Yeah, not many. Number? 30? 13. 13 offices make money. That means that we're not very good at this. We're not very good at this in the United States, and maybe your numbers are better here. The top 13, including Wisconsin, Stanford, the usual players, MIT, and Utah is among them. We can make money, and we all have different models for doing so. And that's an interesting story, and I'll try to tell you a little bit about that. So at the University of Utah, we started the same way almost everybody else did, with the attitude of throw it over the wall. That is, the idea is that federal governments would throw money over the wall to the university, and the university would just create ideas, create inventions, and throw them over the wall, and would just see whoever would take them. It was a random process, and in fact, it really didn't involve much personalization. It didn't involve much engagement. It was a throw it over the wall process, and that's almost all universities did this until we had what's called the Bayh-Dole Act. The Bayh-Dole Act came around in the late 80s. By Senators Bayh and Senators Dole, the same Dole that ran for vice president on one of the presidential platforms. And their idea was that the National Institutes of Health in my country was the largest single patent generator and the largest purveyor of research capital money in the world, and yet fairly not productive in terms of getting that research value out to the American public, getting return on the dollar back to the American people whose taxpayer dollars pay for research. So the Bayh-Dole Act said that for every university that received a federal grant, that the university had free title to exercise and capitalize and exploit the intellectual property that was developed by a federal grant at that university, even though it came from the National Science Foundation, the USDA, the U.S. Geological Survey, the National Institutes of Health. Any federal agency that gave the university a grant, the university had title to all intellectual property that was created by that grant. And all of a sudden the university said, wow, we can take federal grant dollars and we can make money from the intellectual property that's generated from any federal grant on our campus. And that really revolutionized the thinking, and we see an increase, an exponential increase in the amount of startup activity and things that happened then in the 1990s. So between this throw-it-over-the-wall mentality that started in the 1970s, in the 1990s we started to see this exponential increase in the amount of commercial activity that was going on at most universities. And most universities were very bad at it and continue to be very bad at it, but at least there's this effort to try to engage and produce value from rote research dollars. So at Utah, the startup phase began in about 2005, and that's the idea of, okay, we can form companies, and the objective moved from simply a defense posture of protecting our intellectual property, not knowing how to make money from it, not knowing how to get patent revenues back, not knowing how to get any kind of value in the marketplace, now actually trying to then create and form companies, and we had what's called the Kickstart ecosystem. That is, kickstart companies, kickstart professors into commercial engagement, start to teach them how to build their inventions, how to build this value, and try to return some of that investment to the university. In 2011, this morphed into actually producing value in a system-based process, and this moved from simply creating companies to actually growing companies within the university, keeping the company in the university. And I'll show you why in just the next slide. What meant this growth label here, and then most recently, the universities tried to actually be an equity partner in the company, not only keep the company within the university as long as possible to build value, but also be the champion, and I'll show you some of the tools that are involved there. So it's been an evolution. There is no perfect system. I'm not the rah saying Utah's the only way. It's one way. It's one of the ways I've experienced and I've been happy with, and I'll try to then describe this more. So the commercialization process is taken right off the technology venture office's website at Utah, is to disclose, but in fact, as disclosure, there is no value to the invention. Nothing's been proven in the marketplace. You meet with the TVC people in our technology transfer office to try to figure out what that value is going to be. Then you assess the value with the TVC. That means we have to understand prior art, have to understand who has competing ideas in the marketplace. Is there a way to patent? Is there a freedom to operate? That's a key word. Patents don't enable freedom to operate. Freedom to operate is distinct from patents. And so then the idea is to say, okay, if there is freedom to operate, then let's protect the idea and assert that freedom to operate. Through the freedom to operate, then, the invention is de-risked, and this is actually one of the key features that builds value, and this is why the University of Utah's program, I think, is very unique, is because they try to help the inventor keep control of the idea and keep the idea within their lab as far as possible to de-risk it, because by de-risking the idea, you can assert to somebody on the outside that they're getting what they pay for. An early stage idea is always high risk, and until you de-risk it and show the intended customer on the outside that you have what you say you have, that it works the way you say it works, that it functions the way it can work, and that they can understand their time to market, their profitability, their attempt to get their money back, then that de-risking process is essential. So this de-risking, we try to keep it in-house and try to then de-risk it here. We partner once it's ready to partner, and then we take it out. And I'll give you some more details. In order to do that, we have then various entities within the University of Utah. And so, for example, the School of Business has underneath it then several components that are institutes within this School of Business. Pierre Lassonde is an amazing entrepreneur who's been a catalyst at our institute to produce an invention center, an entrepreneurial center, and put his name then and branded this after his donations and his support of this effort. The Eccles School of Business, of course, has an entrepreneur and strategy department now. The Sorensen Center, all of these, of course, are named after high net worth wealth individuals who have given huge donations to the university, and therefore these things are named after them. So this is all within the School of Business, and then of course supporting that is our Technology Transfer Office. Here the Health Sciences has its own Center for Medical Innovation, in which I'm a part, and the Engineering School, in which the Department of Bioengineering sits, that I'm a faculty member, has then an Engineering Innovation Center as well.
Father and son in the middle column?
Yeah, this is father and son, James Lee Sorensen, and the Sorensen family has numerous people, but this was a family that was engaged in biomedical blood contacting catheter development. And you might know that Utah has C.R. Bard Vascular Access, Edwards Life Sciences Vascular Access, Becton Dickinson Vascular Access. All of those huge companies are sitting in the Salt Lake Valley. And Sorensen played a major part in developing several innovative components to catheter and vascular access devices, and they made a lot of money doing that. All right, so we have this innovation ecosystem. This is a common buzzword these days. Our innovation ecosystem then comprises our Technology Venture Office, the Center for Medical Innovation, the Center for Engineering Innovation, and the Entrepreneurial Faculty Scholars, which is a club, so to speak, of faculty who believe that it's important to translate ideas and to get them out there so that the public can enjoy the benefit and that the university can enjoy the prominence of the inventorship, the joy of inventing. In addition, then, the Vice President for Research and Enterprise Office is involved, and the Lassonde Entrepreneurial Institute is involved. We have what's called the Corporate Concierge, which is an interface with the outside world to allow then companies who are interested in finding new ideas to come and interface with our technology, thumb through virtual Rolodex files of ideas and invention disclosures, see things that they're interested in, engage with the faculty in a formalized process. And then we also have then other ways that the campus gets involved, and I'll try to show you how students are formally involved in this entrepreneur and inventionship process. So here's this value curve I showed you. If we look at this y-axis in terms of money spent or money of value on an idea, and the x-axis is the time of the idea as it evolves, an early stage idea has then basically, the gray dotted line is on the double y-axis is risk. So this dotted line indicates that at a very early stage in an idea's development, there's a lot of risk with that idea because it hasn't been debugged. It's early stage for a reason. And as you progress then in time, you spend money inside the institution and your lab. And as you spend money and put student and postdoc time on that idea, then you de-risk it and you take it down this curve. So you're spending money here in red, cumulative spending, and you're de-risking at the same time. How do you do that? Well, you have research grants, and the research grants go to your lab, and the university is just asking you to do your job. And you do your job as a professor, you do your job as a student, you do your job as a postdoc, and the money gets spent off the grants, and the idea comes and becomes more formative, gets more solid, gets more established in terms of what it is. So the university can track the value generation by this ratio of how much you've de-risked the idea to how much money you've put into the idea. And the value of the technology shown in green builds as the risk goes down and as the money goes in. So now the idea is, all right, we want to capture as much value as we can. Why give the idea out to an industry here when the value of the idea could be built and we could sell the idea for much more money here? So if we take a integration or an interpolation of the amount of money we spent on the idea versus the amount of value that we're building, you can see that they diverge at an early point, and that we can, in fact, for quite a not much investment, we can actually build the value substantially. So the question becomes, when should we think about licensing the idea out of house? Should we do it here? Should we do it here? Should we do it here? Or even here? And the idea is to try to then keep the system in-house as long as possible using very little money, because it's leveraged against university resources. It's leveraged against university know-how. It's leveraged against the professor and the students who already know the idea and what they're doing. So to keep it in, then we can build value without a lot of cumulative spending and make some rational decisions about when would it be ready to leave the house, the house. And the technology transfer then at the proper time would be the decision. So there are reasons then to think about timing and strategy to keep new intellectual property within the university. What might those reasons be? Well, we can build value by simply developing the study as a PhD thesis using grant money. We don't have to need investors from the outside. We don't need to find new wet lab resources that are expensive. We can just use what the university already offers us. That is a very huge incentive to keep it in-house. We can de-risk this very easily by using the existing resources and the strengths. And by doing that, we also then can tell somebody on the outside what are the strengths of our new ideas, what are the weaknesses. And by doing this de-risking, we also discover new things about our idea and possibly then generate even new patents or continuations in part of an old patent and extend the old patent's life with new possibilities by having this be even further discovered. Keeping it in-house maintains the inventor's control. We don't have to worry about outside investors telling the inventor what to do or how to do it. Keeping it in the emergent phase, there's a lack of product definition, so as we de-risk this, we actually move from an idea in a concept phase to a much more established product vision. We know what this idea can do. We know what the discovery can enable. So there's a lack of product definition, so if we keep it in-house, we can then actually assert what that product might eventually be. And the last one, of course, is obvious. If no one's interested on the outside, if there is no partnering opportunity, you have to keep it inside and try to keep it alive so that you can develop it without that outside resources. This is kind of a desperate phase to be in, but if there's no apparent partner, you have no choice. All right, so on the opposite side, what are reasons then to take the new intellectual property and give it away, or sell it away, or partner it away? Well, you might have an eager licensing partner out there. There might be somebody waiting saying, oh, I really want that idea. That's a great opportunity. There might be also value that's already been already optimized. You've already done as much as you can in-house. You've got to the point where you have to do a phase 1 clinical trial, and you don't have $1 million, $2 million, $4 million to run a phase 1 clinical trial. The IP is already established. It's already mature. You know what the product's going to be. You know what your patent position is. It's ready to go. It's a kit. It's already solid product idea. It's ready to go outside. And it might be too costly to keep in-house. There's no more resources in your grant. There's no more resources or patients in the university. It's time to try to get it out. So, a startup. Why make a startup? So in our country, we have what's called small business innovation grants. These are grants that come from either the state government, for example, Utah, or the federal government, and they only are awarded to new businesses. Businesses with net revenues of less than $1 million and less than 10 employees, for example, one arbitrary definition. So these new small companies can qualify for what's called small business grants. I can't get that grant as a professor, but if I make a small company with my idea and my patent, and the university gives me the right to operate with that, I can then qualify for monies outside the university. I'm the same person I was inside, but now I'm outside in my own company, and as a professor, I now become a chief scientific officer of a small company, and that company can now receive monies for translating, and that capital is non-diluting. That is, it's a grant just like the university grants are. The grant to the company doesn't have any stockholders attached to it. It's associated with the state revenues or my country's federal revenues, so those grants are non-diluting. So I maintain control of my company. No investors are coming in. I get grant capital to operate. So a startup qualifies you for de-risking under a non-diluting option. And that's very important because you maintain your inventorship position without the exploitation from outside investors. All right, so here's then the Utah startup numbers, and you can see how the Bayh-Dole Act has influenced this as a function of year 1970. What happened there? 1970 here, and about 2000 here is when things started happening. And so you can see this exponential jump in the numbers of startups. And up here then it shows, and it's difficult to see, but it just basically shows the diversity of the startups through the university. That in fact the College of Fine Arts, that's dance and graphic arts and so forth, had startups. The mining and earth sciences had startups. The School of Medicine, of course, enjoys the majority of the startups, but even the social and behavioral sciences had a startup company come out. So anyway, it's very interesting, the diversity of the startup revenues and the startup activities that have come to the university over time. So prominent ones you might recognize. Myriad Genetics, that's the BRCA1, BRCA2 gene fiasco, the subject of the Prometheus gene lawsuit, the Angelina Jolie breast diagnostic that caused her to get an elective double radical mastectomy. That oncogene company was founded in the pathology department next to my lab in the medical school, and made a lot of noise and made a lot of people a lot of money out of the university. This ARUP, the Associated Research University Pathology Laboratories, is the largest single mail-order pathology lab in the world. They process 7.5 million samples per year. They run 24/7. They employ 2,700 people around the clock every single day of the year, doing biopsy analyses, ELISA assays, immunolabeling, histology, all kinds of stuff. All mail-in samples, frozen, shipped by air to Utah, and then read and processed on site. BioFire was the founder of the light cycler that was sold to Roche. So the PCR light cycle machine, if you ever used any PCR, that was developed at Utah. Roche bought it, and now it's called BioFire. All right, so there's some other things. The fentanyl lollipop for pediatric anesthesia, pain relief, also for cancer patients in the form of another fentanyl derivative, Actique. So Cephalon bought both of those fentanyl products. NanoString is a DNA sequencing platform in which my surface chemistry and some other bioinformatics technology has been licensed out of Utah. And then Biotime is the licensee of these high hyaluronic acid hydrogel biomaterials, in which Jade Therapeutics, the ophthalmic company I talked about earlier, basically uses the same materials there. So what's interesting about then our licensing activity is that if we plot this as a function of two arbitrary metrics, financial success, where more success is up here, least success is down here, and then efficiency of licensing process, where most efficient is over here to the right, and least efficient is over here to the left. And we then take some very famous 140 companies from around my country. Some of them are vaunted biomedical institutions like Duke University, Johns Hopkins University, MIT, Mayo Clinic, Caltech. And so this is the sweet spot to be in, this upper right quadrant, where you have the best financial performance with the best efficiency. And you'll notice that tiny little Utah sits right here in a very nice quadrant in terms of most efficient process of technology transfer with the most financial benefit. So we have then this to go, and there's some surprises here. The Dana-Farber Institute is not so impressive. Sloan Kettering's not so impressive. Fred Hutchison. So it looks like the cancer institutes in general are not very good at producing financial success from their technology transfer efforts. All right, here's a snapshot from the Center for Medical Innovation website, and it basically is trying to advertise this idea that every year Utah has over 200 faculty inventors that are trying to translate their technologies, and I'll get into that just in a second. But the point is that we try to make it easy for faculty. You'll notice that these buttons say why faculty should get involved. They have here, for investors, a hot button here. For faculty, if you're interested in being an inventor. For students, if you're interested in being a student inventor, here. So these drop-down tabs will actually tap you into the entire process and the resources for how you can think about moving forward. Total research funding at the University of Utah is modest. I would say this is an average for what we call a Type 2 research institution in my country. $400 million in externally funded research per year. It is what it is. I'm just trying to calibrate you. In terms of how the research breaks down in our university, most of it, of course, is held by the medical school. The College of Engineering has a modest fraction, but the Department of Bioengineering actually has a substantial amount of this fraction here. So biomedical engineering and the School of Medicine Biomedical Sciences have actually a very large lion's share. I work also, my primary appointment as chair of the pharmaceutical chemistry program is actually in the College of Pharmacy. We're the smallest college of pharmacy in our country, and yet we're the fourth ranked in terms of annual research revenues. So a lot of this College of Pharmacy financing per year comes comes and is actually leveraged by the School of Medicine financing and by Bioengineering. In fact, 4 faculty in my department, including myself, are jointly appointed in the School of Bioengineering. So we actually have a foot in the medical school campus and in the College of Engineering. I think that's a huge strength. In terms of invention disclosures then, we see as a function of fiscal year that we have approximately, on average, 200 invention disclosures per year from my university. I don't know if that's a high number or a low number. I just give it to you to calibrate. And disclosures and patents by college then, if we think about the School of Pharmacy, the School of Medicine, the College of Science, Nursing, and Engineering, and Dentistry, we see then the breakdown of how disclosures and patents distribute out. So again, the School of Medicine and this College of Engineering have the lion's share of what happens at our university. There's some surprises, though, in terms of the numbers of disclosures nationally speaking versus the millions of federal research dollars. Remember, Utah had about 400 million research dollars. So sitting right here is this dot for the University of Utah, and we have about 200 invention disclosures here. And so this is where we sit, but if you want to compare to, for example, the University of Wisconsin or Stanford or Caltech or MIT, that, of course, there are institutions that get far more disclosures per unit dollar, and then there are other universities that have far less disclosures per unit dollar, here bracketed by these 2 lines. So our goal is to push ourselves up this way, where the same amount of revenue, because it's relatively flat for our university, the same amount of revenue will actually push us and get actually more disclosures per year per unit research dollar spent. In terms of numbers of patents per year, we have relatively flat over time, steady stream of IP. And so the question is that each one of these patents costs about $25,000 to get. The university doesn't have that money just to throw around. There's no value in a patent. The value of the patent is what it bears in the marketplace. So we have then the idea that if we're spending $25,000 times 75 a year, how are we getting that money back? And so I can tell you that when a patent is issued in my name, that there's enormous pressure on me to go figure out how I'm going to get that money back. It's not just the University Technology Transfer Office's job. It's my job to go beat the bushes and figure out how I'm going to get the money back for that patent. It's a privilege for me to get that patent. It's my job to try to get that back. All right, so in terms of the patents by type, here's where I work: therapeutics, pharmaceutical, drug delivery. I also work here, medical devices, and I work here in diagnostics. So this actually is the lion's share of the types of patents that come out, and I have patents in each of these areas, but there are also other things, and I'm not so conversant with what goes on. I sit on a technology evaluation committee. I know that your committee meets tomorrow at 10 o'clock. I sit on that same committee for diagnostics, medical devices, and pharma, to evaluate technologies for my peers that comes out at the University of Utah. In terms of licenses, so remember, the only way we get money back is by licensing it. So we have now 90 licenses in 2015. And what's important, I think, instead of understanding the number of licenses, that may be a high number, maybe a low number to you, I don't really know, I don't put a judgment on it, but what's important to me is that 57% of these licenses received internal support. Remember this idea of building value inside. So it could be that we have then this number of licenses because our university is willing to push dollars, and it's relatively small amount of dollars considering the investment. Number small dollars, but by pushing, remember, that early stage idea up the value chain, it allows us then to produce more licenses because we've de-risked the technology, keeping it in-house with non-diluting, non-investor dollars, using infrastructure within the university, and can get then these numbers of patents up. Then what's interesting is that these patents, once they're licensed outside to startups, that these startups have then generated $1.7 million, again, in non-diluting federal small business grants. So this we're talking about then investments that are not from investors, but from federal economic development agencies, so that we leverage that amount of money plus that to get these licenses out. And we haven't even had an investor yet dilute the company with outside cash. So I think that's important to think about, that leveraging. And every time I gave a talk in Otago, you ask then, what is the Dunedin government or what's the Otago government doing to help leverage ideas from within the university to get out? And the difference between what we have at Utah and what we have in Otago is huge in terms of the relatively small amount of resources in Otago and Dunedin that help us with these types of activities.
Sorry, do you want to go over a bit more detail about those numbers?
Yeah.
So the 650 is per company, per project, pre-incorporation.
No, this is an aggregate. Yeah, this is an aggregate amount of internal cash that's pushed to whatever companies qualified here to get that cash. In other words, you could say this is distributed over 90 licenses, but in fact it's not that. It's probably 23 of these licenses received that money over 3 years. So while we have 90 licenses, 57% of these received this money over 3 years. Total internal money. All right, let me try to be
Investment from the university, not per project. It's 650 over
Yeah. That's total money for the university. So I know, for example, in my case, I received $40,000 once, and I received $55,000 again to support a student or a postdoc for 1 year each. So I received $95,000 that pushed my project out to the point where it could be licensed.
And where does the money find? Where does the university find that money? Is it from your tech transfer profit?
It comes from the Tech Transfer Office. It comes from revenues that are generated by the Tech Transfer Office from other licenses, and also probably there's a piece from the Vice President for Research Office here annually that's renewed.
So that seems quite light in terms of your institution. So your institution is spending $200,000 per year across all your projects?
For this particular mechanism, yeah, for this particular mechanism. $200,000 per year, yeah, probably. Because if there's $40,000 given, and I'm on a committee that determines 5 of those awards, probably. That sounds correct.
Whereas Auckland Youth Services have put maybe $1 million.
Okay, yeah. So our university's 23,000 students, about 1,000 faculty. I don't know what you have, but
those federal state technology grants, so you have to incorporate before you get those, so you can incorporate without any external investment.
Correct.
So you can form a company and the offices are all drawn from the university, and that then gets you a federal grant.
That's correct. That's correct.
And that 1.7 is spread over all your companies?
That's per year. And I could go, if I go to the next slide, sorry, if we go to this one. So if we look at commercially sponsored research revenue is about $14 million a year. And that's 33 engine investments. Those are the type of investments that are 40 to 50K per year. And so that's $394,000 in internal university investments from the TVC office. So those are actually different numbers than here. So this is taken straight off the website in 2013, as I recall. Yeah, 2013 by the numbers. So we had, again, 212 disclosures, 409 inventures, 89 licenses, and those then generated $14 million in outside commercial investment, including $400,000. This is in university investment in the idea at an average of 12K per. 39 government grants that were producing this amount of money, and $6.35 million in total government grants. So that must have been, I don't know, I have to reconcile these figures now. You now made me question how I got these numbers. I wrote these numbers from an internal document, and now this is on the website and it shows different numbers. But okay, whatever they are, I haven't given this talk enough to think about the fact that this number is different than that number right there.
And the number from the government will give you that without any matching private investment, so that's just a research fund.
Right.
As soon as you incorporate it.
Yeah, so there's actually come in phases. So phase 1 is $250,000, up to $250,000 for 6 months, only to the company. Phase 2 is $1.25 million for 2 years after you pass phase 1, only to the company, no matching required. Make sense? Okay, I'm sorry, I got to fix that, but I don't know the answer. So to move on now, so how does this work? The Commercialization Engine at our technology venture office here in Commercialization Office is called then, the engine, it's got several stages, and frankly, this is all business speak, and I'm not really interested in moving forward in this talk right now, given where we are with this. I want to get to other components of this. The idea is that there's a 2-cylinder, a 4-cylinder, and a refinement process. So it's called here the 2-stroke process is this early stage we have an invention, but we don't know what it's good for. So this is a block of granite. And so here's a man conceptually melding the block of granite into something that's going to come off the end. And when it does so in its later stages, this seemingly ill-defined, poor object will be then refined into something of higher value. So, of course, it's conceptually true. We have an early stage idea that has no real product definition. And the process then of the technology venture process is to produce a product definition of higher value than simply this block of granite. So the technology is disclosed. Milestones are then sought. And this timeline is what takes the early stage product to the milestones there. I'm not going to... So the idea is to take this early stage and to watch it develop here, watch it develop, and then, of course, then you have this highly refined idea at the end. And conceptually, that's how our TVC office drives this. I want to move beyond this, though. So, yeah, this has a lot of meaning to certain people. I don't want, unless you guys are interested, we can come back to this later. So the last part of this is to execute and actually take then this finished product and get it then transferred out of house. The technology moves to the hands of the licensee once it's refined. So we try to keep it in-house this whole time. And the TVC engages licenses in their process to try to get this product taken out. The milestones are met, successful commercialization. The TVC office chalks up another success and moves back to the inventor. So between the university invention and commercialization, just to sum this up, our office then has this idea of the normal technology transfer office value added. That is, the value of the technology in most technology transfer offices stays flat. It's only in this very late stage that the value is defined because the product gets defined. And so our university wants to keep the product until it reaches this point, and then commercialize it because we capture all of this value that we have in-house. So the TVC at our place value adds by keeping the project in-house. How? By providing resources and encouraging us to keep it in, and providing then incentives for students and postdocs to be funded by the PI, and they give us small engine funding, these $40,000 or $50,000 grants, to keep it in-house and encourage the students who know what they're doing, the postdocs who know what they're doing, to help the PI get the project advanced. So the students are equally engaged. We have students who are inventors on patents all the time, and they also are benefits factors of the royalty stream that accrues from that. So we capture this value that is normally, if you out-licensed right here, you would never capture this value. So at the same time, we know that with a startup company in Utah, it's difficult to engage a management team, a CEO, a CFO, high net worth individuals to come in. They don't want to really come in and engage in management because the value of the technology hasn't been defined, and also the product value proposition in the marketplace hasn't been defined. It's difficult to manage. So the university will step in and say, all right, we will try to be the manager, to keep your company concept operating. Our university will step in as a surrogate management team and hold both the capital resources and the management structure in-house to help us form that company. So the typical TVC management engagement starts here, after they've invested in the engine, after they now think, okay, we have something we're going to incorporate, and our technology transfer office actually becomes our management team, because it's difficult with no resources and with no outside money to produce a management structure. So then, by engaging a management team from our university's technology transfer office, we can then capture this value, hopefully, that otherwise would not be captured if we had to out-license at this point. So we try to capture and keep it in-house at this point as well. And by doing so, we then get this return on investment back that we otherwise would have lost had we continued to fund the idea. We would have lost the return on investment by licensing it out here. So we try to keep this value in. So the sweet spot then for our research foundation to engage outside management is, after they formed a management team inside, capture this value. Then the idea is that we've already de-risked it. The value of the invention starts to go up. So now we can start logically to seek management structures from outside. And this is also much more pleasant and much more attractive for someone from the outside to come in, because a lot of the higher risk parts of this idea have already been de-risked inside. All right, so what's needed then to move forward? To be more successful, do we continue to throw more money? I mean, most faculty say, oh, just throw more money. We just always need more money. We're just this consumptive parasite that never is satiated. But do we need better operations? Do we need better ideas? Well, I mean, at some point, yes, all of this is important to get licenses outside, but the key is getting de-risking partners. De-risking the idea seemed to be, for us, the biggest deal. Asserting freedom to operate, asserting what your product definition is, asserting that it has technological capability to meet the unmet need. So the biggest block is finding the right people, and by finding the right people, you've got to de-risk the idea. All right, let's talk about student engagement for a while because it's very important for me. Students engaged, undergraduates and graduate students are engaged. We have team building across many departments. We have a streamlined process and a formal management structure to keep students engaged. We have a student innovation contests. We have energy and engagement from multiple places within the university. We have an entrepreneurial program at the undergraduate level. At the graduate level, we have a medical doctor, Masters of Innovation degree for medical doctors. We have all kinds of different degree programs now, and we have funding that's thrown at this to allow people who would normally not have an interest in entrepreneurship. We have funding to help them get through their degree as an incentive to do that. Let's look at this quickly. So this is the typical propaganda that's pitched to undergraduate students because they have no idea what an innovator is. They have no idea what an entrepreneur is. So we try to tell them what the type of personality and phenotypic embodiments are with the typical student who might want to be engaged. So we started this kind of propaganda process in 2002. To say, you know, who do you identify with in terms of your properties and your interest in doing this? In 2006, we started an ideas competition, and it was called Bench to Bedside is one of them. The Utah Entrepreneurial Challenge is another. And we have then local sponsorship for example, students may win $40,000 for their business plan in an entrepreneurial contest, and that money is not personal money. That money is only guaranteed to you if you incorporate, form a company, and you'll get $40,000 to enact your business plan as a business, not as an individual. We send several people to the Undergraduate National Collegiate Inventors Competition every year, and so in 2006, we had these kinds of numbers, and we received over $100,000 for, this is for undergraduates, to be funded, 48 teams, 33 different majors. You can see the majors shown here. And there were several different types of ideas that came about. Utah is a huge home to the recreation and sports industry, so there's a lot of sports ideas, including skiing and so forth. But this has now morphed, and we received national recognition as this has moved from 2006. 10 years later, 2016, we've been recognized as a top 25 program in student engagement. We actually had students appear on Shark Tank, which is this ABC nationally televised show. I think there's a New Zealand version of this, I think. We have some interesting, for example, this power pot company. These people take and make a steam engine that you can heat on a wood stove. You can power your laptop, or you can recharge your iPhone just by putting a pot of hot water on a camp stove and a fireplace, and they make all kinds of other things that are wilderness-based power accessories to recharge your electric doodads in the middle of nowhere. There's other things that have been, I'm not going to go through these technologies, but lots of other, you have similar slides on your website as well. In 2012, top 25 program, 50 student scholarships, over 1,000 students involved, and now the numbers of different programs involved in the state of Utah have been widely expanded. And the other testimony is that we have then upped the ability to get jobs. As you know, Rio Tinto is the largest Australian mining company, one of them the largest in the world. Bard is the largest manufacturer of cardiovascular, endovascular equipment. Gore, as you know, is a medical device company. Stryker, a medical device company. So our students actually are going to high value-added jobs. Disney decided to put a graphics animation studio in Salt Lake City based on the graphic arts and numbers of software apps that have been developed by our students at the University of Utah. So this whole thing has produced now this mindset at the university where faculty inventors are well known, but now student ideas are overlapping with faculty inventors, and the community is engaged because we have then lots of different competitions, and it's PR is very visible. So we have this kind of integrated network that we're trying to then have students think that they are in fact empowered to invent. They're on patent applications, they're on business plans, they're on new company names, and as an undergraduate, it's been very real that they can take their ideas and make them into value in the workplace. So what's also new is that we've created then this entrepreneur and strategy department within the College of Business, created in 2014. 3 endowed chairs, 5 tenured faculty, so 8 new faculty positions and 8 research faculty positions in this entrepreneur and strategy department. And the degree options are you can get a designation on your diploma, a certificate on your diploma, a minor, a major. You can major in entrepreneurship, you can get a graduate degree, and you can move it and partner it with an MD, partner it with a PhD if you want. So I have 2 students in my group who got PhDs in bioengineering, and they added then either a certificate to their PhD, or they added actually a graduate master's in entrepreneurship to their degree. Very flexible. So in addition now, we can add on this new box, which is all of these different degree programs that validate student training, where they can show that they got training on their diploma, and actually they get the real experience to do so as well. All right, so I'm going to skip through this. And so I want to go and show you some examples here in closing minutes. And what I really like to do, because Jill is still here, I want to go through. So here's a quick example. This iGate technology. So Jade Therapeutics was founded in 2013 by these 2 women, ophthalmologists in the medical school, and I was the biomaterials person. It was formed as a privately held company with ophthalmic drug delivery. They made these plastic thin films that go on the eye, not in the visual circle, but down in the lower part of the eye, and they only release drug for 2 to 3 days. And so the ophthalmic delivery company produces then these extended release drug formulations, only 2 or 3 days for antibiotic, to avoid people having to put drops 6 times a day in their eye if they have eye surgery. This is the biggest problem with the eye drops, is compliance. So the idea is we could just put the antibiotic in this film, put it on eye, and it would dissolve after 3 days and go away. So the intellectual property was basically, we purchased hyaluronic acid from a Utah company that was already spun out of the Department of Bioengineering. We made these degradable gel thin films. We loaded them with drug in my eye. There's 5 employees, really 4 consultants, and this woman as the CEO, Chief Medical Officer. And there was really no cash involved. We were all paid in stock equity to function, except for 2 hourly scientists who were my students. And so therefore the burn rate was exceedingly low. It was all just work on paper, except for these 2 scientists working in my lab. And so the initial funding was a private angel round with Inner Circle friends to secure those 2 technicians to drive the idea forward. We used to secure the IP for this idea and the initial technicians in space. And then a Series A round of 1.3 million. And then we applied for many grants, NIH, NSF, and Army grants. Why? Because they're non-diluting. We don't have to worry about outside investors. We just get money, and it's non-diluting. So then in 2016, while I was here, then iGate, which is a publicly traded ocular drug delivery company in New York City, paid $3 million cash for this company. And again, all of these investments were non-diluting, so the return was very interesting for only 3 years in the business. All right, let's talk about this one. This Salute company was started from my lab in 2012, and an angel investor named Danny Farrar, who's the founder of Myriad Genetics, the BRCA1, BRCA2. So he's a serial entrepreneur. He's funded 13 Salt Lake City's companies to date, including Myriad Genetics. Very successful. The history of this company is that the IP is licensed from my lab. The technology is an implanted biodegradable bone biomaterial to fit in a cuffed annulus on the base of a total knee prosthesis. So this is a biodegradable material that releases antimicrobial drug and then goes away as bone grows in around a newly implanted knee prosthesis. And it's to address then the problem of prosthetic infection that is an increasing problem in our patient population. 1 million total knees last year in my country, and 1 to 3% of them infect. And those infections are very traumatic and very costly, up to $250,000 each to fix. And oftentimes, if you get one infection with the total knee, you keep infecting, and you keep infecting, and you keep infecting. So a solution for this problem is not available. There is no biodegradable solution, and there's no extended release antimicrobial solution. So my idea was to address that need of addressing orthopedic infection. So the history of this briefly is that in 2013, the university helped license this by taking an equity position in exchange for covering the patent and licensing costs. So this is an idea. Of course, it's not unique, but it's the ability of the university to say, okay, Grainger can't pay for $25,000, so we'll pay for the patent and licensing costs, but it's going to cost him a piece of the company to do that. In 2013, initial seed funds from this company, which is Denny Farrar's VC company, $750K in 3 tranches came to support then the initial commercialization of this technology. We got numerous economic development awards, about $500,000, non-diluting. And then currently we have a Series A2 round seeking $4.2 million for a pivotal large animal study, and then a commercial manufacturing plan that will get us to a phase 1 human trial. So this $4.2 million round is nearly closed. We almost have all of that money now, and we're going to proceed forward with the pivotal large animal study. And so if you're interested, I have actually the actual pitch slides, because often students are interested in, like, what's the pitch? What's the real world scenario? When you go in front of investors, what do you really say? So I actually have the actual pitch deck here, and I put my name here just to represent you today. Not that I would give this pitch deck. I'm not the person, usually the CEO gives this pitch. But anyway, if students are interested, the real slides are here. I know we're out of time for now, but the important part is that these are real slides pushed in front of real investors, and this is what this looks like. So the first thing in a pitch is to say, what are you pitching? What is the product? What are you addressing? What's the unmet need? If you're an investor in the room, you want to know why I need to empty my wallet for this guy who's up there yapping in front of the slide deck. So, we believe that we have a unique patent-pending technology, a degradable antibiotic bone filler, a sustained polymer-controlled release for clinically relevant levels of 6 to 8 weeks. We believe that we have this and nobody else has that. We believe that also it can serve a large and growing market. It's complete. An animal study is, we've already done a pilot study, and so that the large animal study is what we're seeking money for. That this, if we can get this large animal study done, it will be able to allow us to go to first-in-man studies and regulatory clearance. So the investor pitch is actually to get us through this study and get then into first-in-man and get the product to the market. And we think we can do this because we have an accomplished team. So I'm not going to go through all of these pitch slides. There's like 10 of them. We don't have time. But the market, I'll stop here. The market is to address this problem. The primary joint replacements have 1 to 3% infections. The revision total joints have 8 to 15% infections. So once you get one infection, you will reinfect at a much higher rate the next time. Knee revisions, there's over 54,000 of those in my country. And as I said before, once you get one infection, then you tend to get more. And each one of them can cost up to $250,000 to fix. And the average cost is $27,000. So if we have 1 million and they infect at 1% in the primary case, we know that we already have a substantial market of revision costs to address. Current clinical treatments, there is nothing available. We have anti-infective bone cements that are permanent, non-degradable. We have bone void fillers, but they don't have extended antibiotic release. So because of that, then, they fail to kill bacteria that can remain dormant and sleeping in your wound sites for several months. So this idea that we can deliver drug for a longer period of time and the bone material will degrade, and then is the new solution. So with that, I'm going to stop and not continue with this pitch deck because simply it's unfair. We're out of time. But I'd be happy to answer questions, and for students who want to hang around or anyone who want to hang around and talk, I'd be happy to do that until I have to go home. All right, thanks.
Thanks, Dave. Questions? Jim?
David, that was fantastic. Thank you. I'd love to hear more of this class.
I know.
The biomaterial, how long is it in place? The drug is being released over 6 to 8 weeks.
This one?
Yeah.
Well,
And generally, over what time do you identify materials and ask for?
well, so any foreign body is an infectionitis. That's the bottom line. That's my whole research expertise. So the less foreign body we have surface area-wise, and the faster it degrades and gets out of the way, the better. The more natural tissue is there and the less foreign body is there, the better. And I have slides in my normal scientific pitch for all of this information. We have, 12 publications. But in my normal scientific approach, I show you how a foreign body reduces the body's ability to fight infection. Typically, if we infected normal bone, woven bone like this, with staph, it would take us, as I said in our meeting this morning, 10 to the 6th to 10 to the 8th bacteria to infect a normal bone site like this in a healthy rodent. But if we put a foreign body in, like a piece of metal or a knee implant, we can reduce the infection susceptibility to 10 to the 3rd, 10 to the 2nd. There's almost a million-fold less bacteria to infect a foreign body than it does the natural tissue. This is the mystery. If we could figure this out and why this occurs and why this immunocompromise or inability to fight bacterial infection around a foreign implant, there's a lot of opportunity there in many device classes, soft tissue, hard tissue, etc. So anyway, here's the answer. The Proastian, this is actually a product from Australia, Biomet product. It's harvested. It's coral and hydroxyapatite, harvested from the Great Barrier Reef. Proastian granules are classic bone void fillers. And so in this defect here, you can see the difference in this MRI between normal woven bone, which is shown in green, and the implant calcium hydroxyapatite crystals, which are shown in orange. After 12 weeks, those crystals have not really resorbed at all. They're still present in the impact site. But if we now take this product, again, green is bone, and orange is mineral. There's like 3 tiny little dots of this mineral here. This whole system, after 12 weeks, has basically started to form woven bone in this implant site. So this MRI, and we have lots of histology to go with it. I could go through the data with you, and we have lots of histology to show the same thing. So the idea is that within 12 to 20 weeks, this matrix breaks down substantially. The drug release is gone in 8 weeks. We know that, and at 20 weeks, a lot of the polymer bone system is resorbed.
And the antibiotics, sorry, I'll shut up and let other people talk on it. Do you vary those, or is that just one?
We've used tobramycin, we use vancomycin. I mean, my academic publications, we've used 10 different ones. Silver salts, lots of stuff. But in fact, I can tell you in the commercial space, companies are only interested in very, very few. And tobramycin is a chief one they're interested in. Vancomycin's the other one. Yes, sir.
Dave, you've had 4 months down at Otago, and so the commercialisation side is very much another theme down there. What do you see as the key differences between the Otago New Zealand scene and what you can experience in Utah?
Yeah, as I told several people this morning, the hunger of outside people to be excited by these biomedical technologies, understand the risk and understand the reward. The fact that in every 10 biotech startups in my country, only 1 is successful, 9 get flushed. Right? So when you put your money out there, there's a 10% win. It can be a very big win, but there's 9 chances that you can statistically lose. So this risk scenario is something that seems that Kiwis seem averse to. And then the other thing is the relative sophistication of shopping. The idea is like, oh, I know that 9 out of 10 are going to fail, but I'm going to go out and shop and do my due diligence, and I'm going to hedge my bets and know that where I'm going to put my money, I have a much better chance of 1 in 10 to do that. And this is where I see that the American investor, at least the people who come and give me money, they're very wise, and they're very well educated, and they've done their due diligence and done their homework. It's not like just going, and slapping $200,000 down a condominium complex at Queenstown. It's a bit different. So there's.
To correct you there, it's far more than $200,000.
Okay. All right. So you're partnered with 20 other people that are each putting down $200,000. But I think when you can make 23% in the real estate market at Queenstown, and you look at something like this, it's a no-brainer. Let's go to Queenstown tomorrow. And so I think there's a certain risk averseness and a certain naivete, a certain unfamiliarity with the kind of biotech investment culture, And then there's this idea that, in my opinion, New Zealand's being spoiled by this real estate market in which there's no other way to spend your money. And I think that unless this bubble too shall pass, right? So the question is, so if New Zealand wants to move on beyond real estate and sheep, what are you going to do? And I think that New Zealand has to think that there's got to be something for our children and our children's children to find high-tech jobs. Otherwise, why am I educating PhDs if they all have to go offshore to find a job? And so I think that I want to understand this problem. I came here to understand this problem. I came here to try to help my colleagues figure out how to empower their students to think deeply, think creatively, create some new IP, and do something with it. It's not your job or my job as faculty always to do something with it. We have perfectly good, viable student engines that can take these ideas, and they can be our boots on the ground. They can be the extensions of our intellect. They know the science oftentimes better than I do in my lab. And so there's no reason why they can't go found their own companies with IP if they're given a process to do so. And Utah's trying to make it as easy as possible. So many things are no license fees, or very modest license fees, or, oh, I know you don't have any cash, so we'll just take a small piece of equity in your company in exchange for a license fee. And that way we can help steward your company as the University of Utah, ensure our investment at the University of Utah, and allow you to operate with very low capital. And the idea is that if we get a lot of ideas out there, because we know that only 1 in 10 might make it, if we get a lot of people out there experimenting with Utah technology, that we'll make it big on the next cisplatin, or the next Gatorade, or the next Taxol. The big wins will return big royalties on the backside to the University of Utah, and there's relatively little pain up front to license out ideas at very low cost just to get people out there experimenting with them. Do you understand that philosophy? So, I mean, this is the difference. Willing to take risk, willing to actually not make a lot of money now, but make a lot of money on a few ideas later, and have creative approaches when people don't have cash. Have some creative approaches to getting the ideas out there and letting people experiment with them. No upfront licensing fees or creative models for licensing that allow your ideas to get out there.
Just a quick question. I noticed that your patent numbers actually reached a peak around 2012 and just have dropped slightly. Is that because you're getting a little bit more demanding in terms of what you require?
That's a good question. Frankly, I don't know the reason for that. Somebody else asked me that, and that's another problem with me coming to Otago with this slide deck that I made and not really knowing the nuances behind some of those numbers. Because I'm not in the technology transfer office, and so I pull these numbers off my website. I do call my technology transfer manager. I have had many discussions about this, but every time I show this deck, somebody like you asks me a question that I really don't know the answer to, and it has to do with the culture of the technology transfer office more than it has to do with me, and I apologize. I just don't know.
Is the University of Utah acting in the University of Utah's interests as a transfer office, or in the state's interests? Is it public good innovation, or good of the university?
Their driver, of course, they're trying to pay for themselves. They are not a for-profit entity licensed by the university. They are all university employees. They're all state employees, so that they are government officials representing getting the best government good for their job. At the same time, they're told a bottom line. Each officer has a portfolio. Each officer tries to make as good on their portfolio performance like you would as a stockbroker, essentially. And so there is certain individual performance parameters and expectations, even though they're trying to act in the best interest of both the university and essentially the state, because it's a state university. So they're public employees trying to do public good with public state dollars and, not be in deficit.
I'm in the technology office upstairs, so it's good to see that we're doing a lot of the same sort of initiatives and work.
Good.
My question is, how do you incentivize the investigators to work with you to get them to bring ideas? And is there a sort of revenue share agreement with the financial?
Yeah, we have the standard third model, right? I think what I'm trying to understand is, what I think we differentiate is in the conflict of interest management, because I'm allowed to have a foot in my lab and a foot in my company and be instrumental in both. But the conflict of interest management is very difficult because you can imagine being in a position of influence that your students in the lab have to know that that you have the potential to bias their outcomes, their degree, and pressure them to get certain results that then make the company look good because you have a financial vested interest in your company. You understand this, but I'm saying this for the edification of these students. By having a foot in both your university lab and your company, you're biased, inherently biased because of the financial leverage that puts on you in your purchasing power, in your mentoring of students, in your mentoring of postdocs, and in your tangible gain that you can possibly get by making wrong decisions or biased decisions. So we have a tight conflict of interest management policy. There's a team that manages each person who is one of these dual inventors, inventor on the inside, then licensing to the outside. There's a team of university people who manages a conflict of interest. I have all kinds of reporting requirements. I have to report in writing to every student in my lab, regardless if they're involved in the technology or not, that I have this financial interest in this company, and by virtue of this financial interest in this company, I could, in fact, exert unfair pressure on you, and I could exert unfair bias on interpreting your results. And if you sense any wrongdoing from me as your PI, then you're immediately to report to this other office over here, and that's my mentoring committee, and they're supposed to know about my conflict of interest. So there are direct reporting requirements, and there's many other stipulations. I know of many other professorial inventors in the US who cannot have one leg in each side of this process. And I feel like that...
Actually, where we're heading for it has been managed, and now they're suggesting it has to be avoided. And so I'd like to...
Yeah, the problem is that it takes the main brain out of the technology. You basically are eviscerating the intellectual engine behind the inventorship, behind the genus of the idea, by taking the inventor out of it.
Conflicts of interest which faculty would have, which are equally as powerful, and we manage those, we should be able to manage this one. And obviously you guys have put a system in place which meets those management requirements.
Yeah, I find it fairly rigorous. I feel like I'm under the microscope. I feel like if I did wrong, I'd be caught. I mean, I have to report quarterly into my my asset values, any assets that have changed, any management structures that have changed. I have to report, how many students are involved in the project, if any. There's a lot of stipulations, and I think it's fair. I think it's transparent, and I think that if I did something wrong, there are many ways that I should or could get caught, and I think that that's fine too.
Pity the same thing doesn't hold in politics.
I tell you, I've spent, since, given the current political climate in the U.S., I've spent most of my free time in Otago trying to justify myself as an American or petitioning for Kiwi citizenship. It's been humiliating at best, let me tell you.
Right, and on that note, let's close.